Go ahead. All right, so we are moving on to dew point and relative humidity. So you do need your reference table out on your desk, okay? And you are going to be using that. So I want the hard copy of your reference table. So either the one that you use, if you have it in your review book, great. If you have it, the hard copy, whichever one you have, I don't want you looking at the one on your iPad, only because you're going to have to actually use it to the best of your ability, and you're going to want to point. You're not going to want to be able to zoom in or zoom out. Okay. So, dew point and also tomorrow is Friday. So what does that mean? It's quiz day. Exactly. It's quiz day. Okay. So you want to be prepared for that. Where is the clicker? Oh, here it is. All right. So dew point and relative humidity. All right. First, we have to talk about the water cycle. Right? You guys have been learning the water cycle since you were itty bitty kids. Right? Here it is. If you Google water cycle, if you want to put this in your notes, otherwise you guys are still responsible for knowing what the water cycle is and all of the vocab words that are on here, like condensation, sublimation, evapotranspiration, evaporation, all of this stuff, okay, you need to know what it means. So something like the word runoff. Runoff is exactly what it sounds like. It's when the, like in this case on the left-hand side here, they're talking about snow melt runoff, right? So the snow is going to melt and it's going to run down the side of the mountain. Okay, when it's talking about running off, it's literally talking about going down the side of a hill, going down the side of a mountain, and picking up stuff as it goes until it gets to a body of water like a stream or the ocean or rivers. Okay? Flora and fauna. You guys know what that means?
No.
Plants and animals. That's all it really means. Flora sounds like flower. Fauna sounds like a plant. Okay? You also have this word here, seepage. Okay? I love when things work on their own. I can't even touch on that. Okay? Seepage is exactly that. It seeps into the ground. And same thing with infiltration. Okay? Infiltration is when you have water being absorbed by the ground, basically. All right? Which means that the ground was permeable. All right? Part of your project, right, talks about the difference between being permeable and impermeable. You either can see through or you can't. There's no in between. Okay? So if you have infiltration coming through or happening, then the surface that it was on is permeable. So something, if you look outside right now, well, actually now is not really the best side, but you'll notice that on the concrete, there's usually puddles of water, right, when it rains. But on the grass, you don't get those puddles of water unless the groundwater is actually up too high. So you guys are responsible for knowing about the water cycle. In general, the water cycle is this. Somehow the water on Earth goes up into the air, gets created into clouds, and it comes down in some way, shape, or form, whether it's rain or snow or sleet. And on the way down, stuff happens to it to get back to that body of water. Simple and easy. All right. So just like everything else, right, you need to have the factors that are going to affect how well something gets evaporated. Okay? The first thing is going to be the amount of energy that is available. We know that in order for you to go from a liquid to a gas, you need a ton of energy, right? Which is why the plateau for the heating curve happens the way that it does. It happens to be way larger than any of the other lines because you need a ton of energy available, right? If you don't, then it's not going to evaporate, right? So we've talked about this before, right? You have those molecules that are in the liquid phase. If it doesn't have enough energy, it's not going to overcome those intermolecular forces of attraction here to become a gas, right? You remember this? Sounds familiar? Yes, no, maybe?
Yes.
Thank you. Okay, so those molecules have to have enough kinetic energy in order to start the evaporation process, in order to overcome those intermolecular forces. Okay, the second one is surface area. Okay, surface area.
Wait, can you go back so I
So
can get the first bullet?
the amount of energy?
Okay. I got it, thanks.
Okay. All right, so the surface area. If I have 10 milliliters of water in a glass versus 10 milliliters of water in a puddle, which one should evaporate faster? The puddle. Why? No, I just because it's more spread out. It's more spread out, right? It has more surface area, which means that you don't have to go through the entire glass, heat the entire glass up, and then have it evaporate. That puddle is going to evaporate a lot quicker than the glass. It's the best explanation I've ever come up with for that is a cough drop, right? If you think about it, right now, hopefully none of you guys are actually sick, but usually around this time, everybody's starting to get flu, or you get a cold, or all of a sudden you have like a tickle in the back of your throat, right? And you need a cough drop, or some throat lozenge that soothes your throat, right? Well, if I give you all cough drops, which I'm not allowed to do right now, right? But if I give you all cough drops, Jared decides to be the odd man out and starts chewing his cough drop. In about 5 minutes, Jared looks at me and goes, "Can I have another one?" Right? Jared now has disintegrated and disappeared faster than the rest of yours, right? Some of you guys stick it in the back of right above your teeth by your gums, right? And it just sits there and it slowly melts. So why did Jared's cough drop disintegrate faster? Perfect. You're breaking it into smaller pieces, which then creates more surface area to come in contact with your spit, as disgusting as that sounds. Okay? When you have something that is in a solid chunk, right, it has to break down the first layer, then the second layer, which is how you get that cough drop that starts out this big to get smaller and smaller and smaller and smaller slowly. The more surface area you have it spread out upon, the faster it is going to evaporate. Right? The third one has to do with the degree of saturation. Okay? This is one of those topics, guys, that you need to know for chem next year as well. So really listen carefully. Okay? There are 3 different types of saturation. It's either unsaturated, saturated, or supersaturated. Okay, so there's 3 different types of saturation. Supersaturation, or I should say unsaturated, is exactly what it sounds like. Okay? When you're talking about the degree of saturation, you're talking about the amount something can hold. So if you have a sponge, right, and you turn on the water, right, and at first, that sponge keeps soaking up water, right? Let's say you just go really quick on that sponge, right? Your hand is not wet, but the sponge is still wet. It's a little wet, right? It can hold more, and therefore, it is unsaturated at the time, okay? So unsaturated means that you can hold more. Okay, I have a couple of examples of this, so if you don't get the sponge thing, get it, okay? Then, if I let the water slowly drip on my sponge, eventually you'll get to the perfect point where you have just enough water on the sponge that it doesn't start to drip out. That's called the point of saturation, okay? It's when no more can be held. There's no more that can actually be held in there, right? If it is saturated, okay, that means no more can be dissolved. No more can be held, okay? My other example to you guys is if you've ever made iced tea, right? You guys all made iced tea from the powder before, right? You ever seen the ones where it's like the single packets? And it's like, oh, just add this, and it's the perfect amount to add to your water bottles, right? Because what they did is they measured out the perfect amount so that there's no sugar that will be left on the bottom, but it's enough that you'll have a saturated solution. Now, some of us, right, like our iced tea super sweet, right, to the point where when you just keep stirring and stirring and stirring and stirring, and there's still little bits of sugar at the bottom of the glass or the pitcher or whatever it is you're making it in, right? You guys have all seen that before? The fact that there's little bits at the bottom tells me I have a saturated solution, okay? Because what is happening is you can't necessarily see it. Even though you're stirring, you're forcing sugar to dissolve into the solution, but at the same rate, what you're doing is forcing one out of the solution, okay? It would be like if we decided to take a field trip, which we're not allowed to do, but let's say we were, and we had to go to the city and take the subway. Not that that would be legal in any way, shape, or form. Let's say we had to, the bus breaks down, we all have to get on the subway. We have all of you guys, and we're shoving each other into this packed subway car. I'm having a heart attack because it's a packed subway car. And all of a sudden we left Valerie outside, and she's standing there like, guys, I need to get on this, right? In order for her to be able to get in the subway car, we got to kick somebody out on the other side. That's how you know it's saturated. Yeah, I have a couple of different examples for you guys for that. It will end up having some of it at the bottom, and to your naked eye, you don't see it happening, where like one morsel is being pushed in while one is being pushed out. Okay, question?
So like, that example I just gave, so like, the sugar would like not be able to dissolve at all?
You won't see it dissolving. The same amount that you have on the bottom, it will be the same no matter how much you stir. You can keep stirring and stirring and stirring. Once you leave it and leave it alone, you'll notice you'll see the same amount of sugar at the bottom. If you add heat, it's a different story, which is how you get to a super saturated solution. Okay? But if you have a perfectly saturated solution and you don't do anything, you can keep adding and adding and adding, but that's not going to dissolve anymore. So that's a saturated solution. So even if you see little particles at the bottom of the glass or the pitcher or whatever it is that you're using, that will be a saturated solution. Doesn't matter how much you stir. Now, if you add heat to a saturated solution, okay, that's when you get a super saturated solution. You force more to dissolve than should happen. So it's almost like you move that line of saturation. Okay, if you add heat to it, more will dissolve. But if you leave it long enough, you'll start to see over time some of the sugar will come out. And that's how, you guys ever have rock candy before? You know how it's like perfectly nice on the stick? You guys can make it at home. If you YouTube how to make rock candy, you basically take a 5-pound bag of sugar and a small pot of water. And you pour some in and you stir till it all dissolves. Then you keep heating it, you pour more in, stir, pour more in, stir, pour more in, stir. After a while, all of that sugar will dissolve because you've added heat to it, right? You take that now sugar-water mixture and put it into a cup that's safe. You pour it in. You can take a stick and you leave it in there. When you leave it in there, and you have to make sure it does not have any sort of disturbance whatsoever. Because if somebody comes by and like knocks into the side of it, all of that excess sugar will fall out. If not, over time, you'll start to see little bits of the sugar come out of the solution and attach to the stick. And that's how you get rock candy. Rock candy is just pure sugar water that is hardened. But so for an unsaturated solution, some more can dissolve, right? For a saturated solution, no more can dissolve. And for a supersaturated solution, you took a saturated solution and added heat to it and forced more to dissolve, okay? So here, right, this is our saturated solution. How do we know? Because you have the rate of evaporation equal to the rate of condensation. So in other words, one molecule of liquid is turning into a gas at the same rate. So in other words, it's doing this, think, 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 back and forth. Okay, and of course this is a closed container because otherwise all that gas would disappear. Okay, this means that the air is now saturated and the relative humidity is 100%. That's what RH stands for. Relative humidity is 100%. Okay, that means you cannot have any more go into the air. Okay, wind speed is going to be another factor because if it is windy, then it is going to bring more unsaturated air into your location, okay? Which means that more water vapor can be evaporated, right? If you have the situation where there is a saturated solution and then wind comes by and gives you more room or blows away some of that water vapor that was in the air previously, then more water can actually evaporate into the air. Okay? So let's talk about humidity. Humidity is not my friend. Because this would be me. Okay, that is not actually me. That's from Friends, for those of you who don't know. Okay? But that usually is why my hair is up in a ponytail on rainy days. Okay? Because it would look like this. And that is just not fun. Okay? So what is humidity? Humidity is the amount of water vapor, okay, per unit of air. Right? There's two ways that we measure it. The one that you're going to be able to kind of do in lab is the Sling Cyclometer. Okay?
Will we be in class for that or not?
You can't really touch anything. So I can show you what a Sling Cyclometer looks like. We would go outside, we would go in the hallway, and we would stay in the classroom and do it. But I don't know if we're going to be able to physically do it unless they allow us to. So far we have not been able to. So the one that we usually use is the Sling Cyclometer. There is another one called the hygrometer that we don't really use as much, at least in school. Okay? So there are two different types of humidity. There's absolute humidity and relative humidity. Okay? Both of which are basically measuring the amount of water vapor in the air. Okay? There's a Sling Cyclometer. Okay? They're basically two thermometers that are taped together on a stick. And you literally walk around and swing it. Okay, to measure to get the humidity and the temperature. Okay, that's a hygrometer. If you've ever seen what are those called? Not a humidifier, a humidor that people keep their cigars in. It's a box and it's got this on the outside to make sure that those cigars do not have too much moisture in them. Otherwise, they do not work as well, I guess. All right, so let's talk about what absolute humidity actually is. Absolute humidity is the mass of water vapor per volume of air. Mass of water vapor per volume of air. Okay, so the formula for it would be grams of water per cubic meter of air. And the units are G/m cubed. Okay, so these are the units at the very end here, G/m cubed. All right, now absolute humidity has a direct relationship with the temperature. Direct relationship with temperature. Sorry, just let me know when you're done, okay? Okay. All right, then we have relative humidity. And relative humidity is going to be the ratio of absolute humidity to moisture capacity. Okay, so in other words, how much of the water vapor is in the container versus how big the container actually is, right? Because the bigger the container, the more moisture that it can hold. Oh, this one's kind of sick. It's kind of creepy. I don't know. It looks like it's got 4 legs and 2 arms. So I have no idea. I think somebody was trying to make a dog, but it kind of looks like a mix between the Joker's girlfriend and a dog. With art, I don't know. Okay. Relative humidity is going to be a percentage. Okay. Now, you can put on your application. Okay. No, that's what I was trying to find out. Keep on. Nope. That's two charts. Nope. So page 12 of your reference table, guys. All right.
Wait, can you go back?
Let me know when you're done, okay?
Okay, I'm done.
Just so you guys know, this is on page 12 of your reference table. Right? So we have to go over all of the definitions before I can actually show you practice problems and how to use this particular one. Where's your reference table? Good news is I'll have it up here. Okay? So it's going to have an inverse relationship with temperature, and this is the one that we're going to kind of be using more. Okay, so what does that mean? If the temperature goes down, the humidity can go up. If the temperature goes down, humidity goes up. Yep, it's an inverse relationship. So if one goes up, the other comes down. Oh. Okay, so everybody has to have page 12 of your reference table out. All right, I'm going to give you the steps, and you're going to put these in your notes. Okay, and then we're going to actually try it using the reference table. All right, so it's Earth Science Reference Table, page 12. See, you see, relative humidity. Be careful with reference table page 12, because both of the charts look exactly the same that are this. You have relative humidity, and then you have dew point. Okay? Make sure you are on the correct one. So remember, always check the titles first, because if this is a multiple choice question on the regions, it will have the answer if you use the correct chart, and it will have the answer if you use the incorrect chart. Okay? All right, so step 1. You're going to find what's known as the dry bulb temperature. Dry bulb is the same thing as just saying the regular air temperature. Okay. Step 2. Remember on that Sling Cyclometer, how I said there were 2 thermometers, right? One of those thermometers at the bottom, when it says dry bulb versus wet bulb, that little, at the very bottom of the thermometer, has a bulb of the colored alcohol in it, the red colored alcohol, right? It's just red dye, okay? On one of those 2 thermometers, you're doing nothing to it, and that's going to determine the air temperature. On other thermometer, you're going to take what's known as a sock. It's basically a piece of cloth that you wet. It shouldn't be to the point where if you start swinging it around, people are getting hit in the face by water, but it needs to be damp. And that is going to be your wet bulb that you're going to use. So you have to read the dry temperature first and read the wet bulb temperature. Then you subtract the wet bulb from the dry bulb. Okay? So then you find the difference along the top of the chart. Okay? Because if you look on your reference table, on the top of the chart, it says difference between wet bulb and dry bulb. Right? You guys see that? Yes, no, maybe? Okay. And then you're going to, on the left-hand side, find the air temperature. Oh, too far. Okay? And then you're going to point to both of them, and wherever the 2 meet, that is going to be your relative humidity. Okay? You are going to take the same steps, whether I'm talking about relative humidity or dew point. To find either of them, you're going to do the same steps. Oh. Thank you. Okay? You're just going to use the different chart. So let's get the notes on this, and then we will do some problems. Okay? What dew point is the temperature at which air is saturated or at capacity. Because remember, no more can be held there. No more can dissolve. Okay? Dew point depends only on absolute humidity, right? The other chart was relative humidity. Dew point is dependent upon absolute humidity. Okay, so when you determine it, again, you're going to use this reference table, Earth Science reference table. But the first thing you are going to do is make sure that you check the title and make sure you're on the correct one. Dew point is the higher one, relative humidity is the one below it. So make sure you are looking at this and keeping that in mind. So let's all look at the dew point, right? You're going to follow the same steps. Right? Notice how on the top here, it says the difference between the wet bulb and the dry bulb temperature. So that's going to be 15 degrees or less. Okay? On the left-hand side, this is going to be your air temperature or your dry bulb temperature. Notice the units. Okay? This is in degrees Celsius. Which means if you have the temperatures in degrees Fahrenheit, you must convert. Or you can look at the reference table on page 14, where you just convert from one to the other. But all of your values need to be in degrees Celsius. Okay? Do not mess that up. So just like when we were doing this for, come on, just like when we did this for relative humidity, right? The steps are exactly the same. Okay, you find the dry bulb, subtract the wet bulb, find the difference, and then you figure out where the two meet. So let me just see something really quick. Right? Since the bell is about to ring, I'm going to do practice problems with you in class tomorrow. Okay? We're going to work on a practice sheet in class tomorrow. So I will post it for you tomorrow morning. I want you to have it ready to go for after the quiz. Okay? Does anybody have any questions on this? Right? It's the same steps for relative humidity or for determining dew point. Just it depends on which one you're looking at. Okay?